Excuse me. All right. So, I've been going a lot slower than I wanted to the last few days. Um, I'm going to say that it's probably the weather. Our weather went from 90s to like 60s overnight. And usually when we have drastic changes in the weather, it takes me a few days to sort of adapt to it. So, gonna keep working on that. Till then, gonna just read as much as I can. Um, I think I have a way to use my voice recorder. I'm gonna start taking that with me to the store every day, and then maybe in between Instacart orders, um, if I'm waiting, I can just go ahead and turn the voice recorder on and do some other stuff that I want to work on. So, I'm gonna give it 1 minute. All right. Mm. All right. Chemistry, Chapter 8, Advanced Theories of Covalent Bonding. 1. Valence bond theory. 2. Hybrid atomic orbitals. 3. Multiple bonds. 4. Molecular orbital theory. Introduction. We have examined the basic ideas of bonding. I'm going to grab some water real quick. Some W. Oh man, I want to teach so bad, but I need to get this done first. I said I promised I would do this first. So, sorry. I did not mean to do that. Okay. We have examined the basic ideas of bonding, showing that atoms share electrons to form molecules with stable Lewis structures, and that we can predict the shapes of those molecules by valence shell electron pair repulsion theory. FYI, those are all models. None of them are actually like the true way of looking at what an atom is. These ideas provide an important starting point, just like it says, for understanding chemical bonding, but these models sometimes fall short in their abilities to predict the behavior of real substances. How can we reconcile the geometries of sp and d atomic orbitals with molecular shapes that show angles like 120 degrees and 109.5 degrees? Furthermore, we know that electrons and magnetic behavior are related through electromagnetic fields. Both nitrogen and oxygen have fairly similar Lewis structures that contain lone pairs of electrons. Yet oxygen demonstrates very different magnetic behavior than nitrogen. We can pour liquid nitrogen through a magnetic field with no visible interactions, while liquid oxygen is attracted to the magnet and floats in the magnetic field. We need to understand the additional concepts of valence bond theory, orbital hybridization, and molecular orbital theory to understand these observations. 8.1. Valence bond theory. By the end of this section, you will be able to describe the formation of covalent bonds in terms of atomic orbital overlap, define and give examples of sigma and pi bonds. As we know, a scientific theory is a strongly supported explanation for observed natural laws or large bodies of experimental data. For a theory to be accepted, it must explain experimental data and be able to predict behavior. For example, Vesper theory has gained widespread acceptance because it predicts three-dimensional molecular shapes that are consistent with experimental data collected for thousands of different molecules. However, Vesper theory does not provide an explanation of chemical bonding. There are successful theories that describe the electronic structure of atoms. We can use quantum mechanics to predict the specific regions around an atom where electrons are likely to be located, a spherical shape for an s orbital, a dumbbell shape for a p orbital, and so forth. However, these predictions only describe the orbitals around free atoms. When atoms bond to form molecules, atomic orbitals are not sufficient to describe the regions where electrons will be located in the molecule. A more complete understanding of electron distributions requires a model that can account for the electronic signature of molecules. One popular theory holds that a covalent bond forms when a pair of electrons is shared by two atoms and is simultaneously attracted by the nuclei of both atoms. In the following sections, we will discuss how such bonds are described by valence bond theory and hybridization. Valence bond theory describes a covalent bond as the overlap of half-filled atomic orbitals, each containing a single electron, that yield a pair of electrons shared between the two bonded atoms. We say that orbitals on two different atoms overlap when a portion of one orbital and a portion of the second orbital occupy the same region of space. According to valence bond theory, a covalent bond results when two conditions are met. One, an orbital on one atom overlaps an orbital on a second atom, and two, the single electrons in each orbital combine to form an electron pair. The mutual attraction between the negatively charged electron pair and two atoms' positively charged nuclei serves to physically link the two atoms through a force we define as a covalent bond. The strength of a covalent bond depends on the extent of overlap of the orbitals involved. Orbitals that overlap extensively form bonds that are stronger than those that have less overlap. The energy of the system depends on how much the orbitals overlap. Figure 8.2 illustrates how the sum of the energies of two hydrogen atoms changes as they approach each other. When the atoms are far apart, there is no overlap, and by convention, we set the sum of the energies at zero. Hold on one second. I'm going to see if I can find my headphones. I want to listen. I want to have a louder noise in my ears. I don't remember where I put them, to be honest. Did I put it up here? Nope. Here? Nope. Here? Nope. Here? Nope. Maybe it fell off the chair. Dang it, did I lose those two? Shoot. Somewhere. Oh well. Oh well. Let's see if I can get the... Sometimes my other headphones are hit or miss, but sometimes they do work. Let's see. Yeah, okay. I can make that work. Ooh, that sounds nice. I can barely hear my voice. That might make it actually easier for me to read. I think when I hear my voice, problem is when it's a large portion of my hearing, I'm focused on it. And when I don't hear it, like right now, I'm not so focused on it. So, yeah, we'll see. I guess I'm going to start rereading from here. When the atoms are far apart, there is no overlap. And by convention, we set the sum of energies at zero. As the atoms move together, their orbitals begin to overlap. Each electron begins to feel the attraction of the nucleus in the other atom. In addition, the electrons begin to repel each other, as do the nuclei. While the atoms are widely separated, the attractions are slightly stronger than the repulsions, and the energy of the system decreases. A bond begins to form. As the atoms move closer together, the overlap increases, so the attraction of the nuclei for the electrons continues to increase, as do the repulsions among electrons between the nuclei. At some specific distance between the atoms, which varies depending on the atoms involved, the energy reaches its lowest, most stable value. The optimum distance between the two bonded nuclei is the bond distance between the two atoms. The bond is stable because at this point, the attractive and repulsive forces combine to create the lowest possible energy configuration. If the distance between the nuclei were to decrease further, the repulsions between nuclei and the repulsions as electrons are confined in closer proximity to each other would become stronger than the attractive forces. The energy of the system would then rise making the system destabilized, as shown at the far left in figure 8.2. Okay, sorry. This music will not do. It's too chaotic. Too many differences. I'm going to go ahead and do the Dragon Age Inquisition main menu theme. Um, that one repeats itself, and it's something that just it gets me wanting to do stuff. So let's see. Oh man, I love the sound of this song though. Makes me want to play this. I actually never beat Dragon Age Inquisition. It goes. I'm gonna start it over and I'll sing along or hum along with it. Mm-hmm. 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 Yeah, I'm not really good at timing myself with this, so I'm still working on that. I sort of taught myself how to make my voice sound a little bit better when doing that stuff, but I still don't know the timing at all. It's sort of, I usually follow along with like a stomp with the foot. I do like a little stomping pattern to kind of see if I can match the rhythm with it. But I don't really have any formal training in music, so that's something that I'll probably have to do at some point. But just the way it sounds, though, it totally gets my whole body just like tingling, I guess. So there's a little figure. The bond energy is the difference between the energy minimum, which occurs at the bond distance. Actually, it almost makes it sound like I'm on an adventure right now. And the energy of the two separated atoms. This is the quantity of energy released when the bond is formed. Conversely, the same amount of energy is required to break the bond. For the hydrogen molecule shown in figure 8.2, at the bond distance of 74 picometers, the system is 7.24 times 10 to the negative 19 joules lower in energy than the two separated hydrogen atoms. This may seem like a small number. However, we know from our earlier description of thermochemistry that the bond energies are often discussed on a per mole basis. For example, it requires 7.24 times 10 to the negative 19 joules to break one hydrogen-hydrogen bond. But it takes 4.36 times 10 to the 5 joules to break 1 mole of hydrogen bonds. A comparison of some bond lengths and energies is shown in table 8.1. We can find many of these bonds in a variety of molecules, and this table provides average values. For example, breaking the first carbon-hydrogen bond in methane requires 439.3 kilojoules per mole, while breaking the first carbon-hydrogen bond in I guess HCH2, C6H5. That almost looks like toluene. Common paint thinner requires 375.5 kilojoules per mole. The reason I say toluene is C6H6 is benzene, and then with a methyl group, which is a CH3, which is that C or the HCH2, that's a methyl. So yeah, that looks like toluene. In addition to the distance between two orbitals, the orientation of orbitals also affects their overlap, other than for 2s orbitals, which are spherically symmetric. Greater overlap is possible when orbitals are oriented such that they overlap on a direct line between the two nuclei. Figure 8.3 represents for two p orbitals from different atoms. The overlap is greater when the orbitals overlap end to end rather than at an angle. The overlap of two s orbitals, the overlap of an s orbital and a p orbital, and the end-to-end overlap of two p orbitals all produce sigma bonds, as illustrated in figure 8.4. A sigma bond is a covalent bond in which the electron density is concentrated in the region along the internuclear axis. That is, a line between the nuclei would pass through the center of the overlap region. Single bonds in Lewis structures are described as sigma bonds in valence bond theory. A pi bond is a type of covalent bond that results from the side-by-side overlap of two p orbitals, as illustrated in figure 8.5. In a pi bonds, the regions of orbital overlap lie on opposite sides of the internuclear axis. Along the axis itself, there is a node, that is, a plane with no probability of finding an electron. While all single bonds are sigma bonds, multiple bonds consist of both sigma and pi bonds. As the Lewis structures below suggest, oxygen contains a double bond and a nitrogen contains a triple bond. The double bond consists of one sigma bond and one pi bond, and the triple bond consists of one sigma bond and two pi bonds. Between any two atoms, the first bond formed will always be a sigma bond, but there can only be one sigma bond in any one location. In any multiple bonds, there will be one sigma bond, and the remaining one or two bonds will be pi bonds. These bonds are described in more detail later in this chapter. As seen in Table 8.1, an average carbon-carbon single bond is 347 kilojoules per mole, while in a carbon-carbon double bond, the pi bond increases the bond strength by 267 kilojoules per mole. Adding an additional pi bond causes a further increase of 225 kilojoules per mole. We can see a similar pattern when we compare other sigma and pi bonds. Thus, each individual pi bond is generally weaker than the corresponding sigma bond between the same two atoms. In a sigma bond, there is a greater degree of orbital overlap than in a pi bond. 8.2 Hybrid atomic orbitals. By the end of this section, you will be able to explain the concept of atomic orbital hybridization, determine the hybrid orbitals associated with various molecular geometries. Thinking in terms of overlapping atomic orbitals is one way for us to explain how chemical bonds form in diatomic molecules. However, to understand how molecules with more than two atoms form stable bonds, we require a more detailed model. As an example, let us consider the water molecule, in which we have one oxygen atom bonding to two hydrogen atoms. Oxygen has a valence configuration 1s2, 2s2, 2p4, with two unpaired electrons, one in each of the two p orbitals. Valence bond theory would predict that two hydroxide or OH bonds form from the overlap of these two p orbitals with the 1s orbital of the hydrogen atoms. If this were the case, the bond angle would be 90 degrees, as shown in figure 8.6, because p orbitals are perpendicular to each other. Experimental evidence shows that the bond angle is 104.5 degrees, not 90 degrees. The prediction of the valence bond theory model does not match the real-world observations of a water molecule. A different model is needed. Here we go. Hold on one sec. Okay, here we go. Nice. Quantum mechanical calculations suggest why the observed bond angles differ in H2O differ from those predicted by the overlap of the 1s orbital of the hydrogen atoms with the 2p orbital of the oxygen atom. The mathematical expression, known as the wave function psi, contains information about each orbital and the wave-like properties of electrons in an isolated atom. When atoms are bound together in a molecule, the wave functions combine to produce new mathematical descriptions that have different shapes. This process of combining the wave functions for atomic orbitals is called hybridization and is mathematically accomplished by the linear combination of atomic orbitals, LCAO. The new orbitals that result are called hybrid orbitals. The valence orbitals in an isolated oxygen atom are a 2s orbital and three 2p orbitals. The valence orbitals in an oxygen atom and a water molecule differ. They consist of four equivalent hybrid orbitals that point approximately toward the corners of a tetrahedron. Consequently, the overlap of the oxygen and hydrogen orbitals should result in a tetrahedral bond angle. The observed angle of 104.5 is experimental evidence for which quantum mechanical calculations give a useful explanation. Valence bond theory must include hybridization component to give accurate predictions. The following ideas are important in understanding hybridization. 1. Hybrid orbitals do not exist in isolated atoms. They are formed only in covalently bonded atoms. 2. Hybrid orbitals have shapes and orientations that are very different from those of the atomic orbitals in isolated atoms. 3. A set of hybrid orbitals is generated by combining atomic orbitals. The number of hybrid orbitals is set equal to the number of atomic orbitals that were combined to produce the set. 4. All orbitals in a set of hybrid orbitals are equivalent in shape and energy. 5. The type of hybrid orbitals formed in a bonded atom depend on its electron pair geometry as predicted by the Vesper theory. 6. Hybrid orbitals overlap to form sigma bonds. Unhybridized orbitals overlap to form pi bonds. In the following sections, we shall discuss the following common types of hybrid orbitals. sp hybridization. The beryllium atom in a gaseous BeCl2 molecule is an example of a central atom with no lone pairs of electrons and a linear arrangement of three atoms. There are two regions of valence electron density in the BeCl2 molecule that corresponds to the two covalent BeCl bonds. To accommodate these two electron domains, two of the Be atoms, four valence orbitals, will mix to yield two hybrid orbitals. This hybridization process involves mixing of the valence s orbital with one of the valence p orbitals to yield two equivalent sp hybrid orbitals that are oriented in a linear geometry. In this figure, the set of sp orbitals appears similar in shape to the original p orbital, but there is an important difference. The number of atomic orbitals combined always equals the number of hybrid orbitals formed. The p orbital is one orbital that can hold up two electrons. The sp set is two equivalent orbitals that point 180 degrees from each other. The two electrons that were originally in the s orbital are now distributed to the two sp orbitals, which are half-filled in gaseous BeCl2. These half-filled hybrid orbitals will overlap with orbitals from the chlorine atoms to form two identical sigma bonds. We illustrate the electronic differences in an isolated beryllium atom and in the bonded beryllium atom in the orbital energy level diagram in figure 8.9. These diagrams represent each orbital by a horizontal line indicating its energy, and each electron by an arrow. Energy increases toward the top of the diagram. We use one upward arrow to indicate one electron in an orbital and two arrows up and down to indicate two electrons of opposite spin. When atomic orbitals hybridize, the valence electrons occupy the newly created orbitals. The beryllium atom had two valence electrons, so each of the sp orbitals gets one of these electrons. Each of these electrons pairs up with the unpaired electron on a chlorine atom when a hybrid orbital and a chlorine orbital overlap during the formation of the beryllium-chlorine bonds. Any central atom surrounded by just two regions of valence electron density in a molecule will exhibit sp hybridization. Other examples include the mercury atom in the linear HgCl2 molecule, the zinc atom in zinc ZnCH3, which contains a linear CCNC arrangement, and the carbon atoms in HCCH and CO2, sp2 hybridization. The valence orbitals of a central atom surrounded by three central regions of electron density consist of a set of three sp2 hybrid orbitals and one unhybridized p orbital. This arrangement results from sp2 hybridization, the mixing of one s orbital and two p orbitals to produce three identical hybrid orbitals oriented in a trigonal planar geometry. Although quantum mechanics yields the plump orbital lobes as depicted in figure 810, sometimes for clarity these orbitals are drawn thinner and without the minor lobes as in figure 811 to avoid obscuring the other features of a given illustration. We will use these thinner representations whenever the true view is too crowded to easily visualize. The observed structure of the borane molecule BH3 suggests sp2 hybridization for boron in this compound. The molecule is trigonal planar, and the boron atom is involved in three bonds to hydrogen atoms. We illustrate the comparison of orbitals and electron distribution in an isolated boron atom and in the bonded atom of BH3, as shown in the orbital energy level diagram, figure 8.13. We redistribute the three valence electrons of the boron atom into three sp2 hybrid orbitals, and each boron electron pairs with an hydrogen electron when BH bonds form. Any central atom surrounded by three regions of electron density will exhibit sp2 hybridization. This includes molecules of the lone pair on the central atom, such as ClNO, or molecules with two single bonds and a double bond connected to the central atom, as in formaldehyde and ethene. sp3 hybridization. The valence orbitals of an atom surrounded by a tetrahedral arrangement of bonding pairs and lone pairs consists of a set of four sp3 hybrid orbitals. The hybrids result from the mixing of one s orbital and all three p orbitals that produces four identical sp3 hybrid orbitals. Each of these hybrid orbitals points toward a different corner of a tetrahedron. A molecule of methane consists of a carbon atom surrounded by four hydrogen atoms at the corners of a tetrahedron. The carbon atom in methane exhibits sp3 hybridization. We illustrate the orbitals and electron distribution in an isolated carbon atom and in the bonded atom in CH4 in figure 816. The four valence electrons of the carbon atom are distributed equally in the hybrid orbitals, and each carbon electron pairs with a hydrogen electron when the CH bonds form. In a methane molecule, the 1s orbital of each of the four hydrogen atoms overlaps with one of the four sp3 orbitals of the carbon atom to form a sigma bond. This results in the formation of four strong, equivalent covalent bonds between the carbon atom and each of the hydrogen atoms to produce the methane molecule CH4. The structure of ethane, C2H6, is similar to that of methane, and that each carbon in ethane has four neighboring atoms arranged at the corners of a tetrahedron, three hydrogen atoms and one carbon atom. However, in ethane, an sp3 orbital of one carbon atom overlaps end to end with an sp3 orbital of a second carbon atom to form a sigma bond between the two carbon atoms. Each of the remaining sp3 hybrid orbitals overlaps with an s orbital of a hydrogen atom to form a carbon-hydrogen sigma bonds. The structure and overall outline of the bonding orbitals of ethane are shown in figure 817. The orientation of the two CH3 groups is not fixed relative to each other. Experimental evidence shows that rotation around sigma bonds occurs easily. An sp3 hybrid orbital can also hold a lone pair of electrons. For example, the nitrogen atom in ammonia is surrounded by three bonding pairs and a lone pair of electrons directed to the four corners of a tetrahedron. The nitrogen atom is sp3 hybridized with one hybrid orbital occupied by the lone pair. The molecular structure of water is consistent with a tetrahedral arrangement of two lone pairs and two bonding pairs of electrons. Thus, we say that the oxygen atom is sp3 hybridized, with two of the hybrid orbitals occupied by lone pairs and two by bonding pairs. Since lone pairs occupy more space than bonding pairs, structures that contain lone pairs have bonding angles slightly distorted from the ideal. Perfect tetrahedra have angles of 109.5 degrees, but the observed angles in ammonia and water are slightly smaller. Other examples of sp3 hybridization include carbon tetrachloride, phosphorus trichloride, and nitrogen trichloride. sp3d and sp3d2 hybridization. To describe the 5 bonding orbitals in the trigonal bipyramidal arrangement, we must use 5 of the valence shell atomic orbitals, which gives us 5 sp3d hybrid orbitals. With an octahedral arrangement of 6 hybrid orbitals, we must use 6 valence shell atomic orbitals, which gives 6 sp3d2 hybrid orbitals. These hybridizations are only possible for atoms that have d orbitals in their valence subshells, that is, not those in the first or second period. In a molecule of phosphorus pentachloride, there are 5 PCl bonds. Those 5 pairs of valence electrons around the phosphorus atom, directed toward the corners of a trigonal bipyramid. We use the 3s orbital, the 3p orbitals, and one of the 3d orbitals to form the set of 5 sp3d hybrid orbitals that are involved in the PCl bonds. Other atoms that exhibit sp3d hybridization include the sulfur atom in SF4 and the chlorine atoms in ClF3 and ClF4+. The sulfur atom in sulfur hexafluoride exhibits sp3d2 hybridization. A molecule of sulfur hexafluoride has 6 bonding pairs of electrons, connecting 6 fluorine atoms to a single sulfur atom. There are no lone pairs of electrons on the central atom to bond 6 fluorine atoms. The 3s orbital, the 3p orbitals, and 2 of the 3d orbitals form 6 equivalent sp3d2 hybrid orbitals, each directed toward a different corner of an octahedron. Other atoms that exhibit sp3d2 hybridization include the phosphorus atom in PCl6, the iodine atom in the interhalogens IF6+, IF5, ICl4-, and IF4-, and the xenon atom in XeF4. Assignment of hybrid orbitals to central atoms. The hybridization of an atom is determined based on the number of regions of electron density that surrounded it. The geometrical arrangements characteristic of the various sets of hybrid orbitals are shown in Figure 821. Those arrangements are identical to those of the electron pair geometries predicted by VSEPR theory. VSEPR theory predicts the shapes of molecules, and hybrid orbital theory provides an explanation for how those shapes are formed. To find the hybridization of a central atom, we can use the following guidelines. 1. Determine the Lewis structure of the molecule. 2. Determine the number of regions of electron density around an atom using VSEPR theory, in which single bonds, multiple bonds, radicals, and lone pairs each count as one region. 3. Assign the set of hybrid orbitals from Figure 821 that correspond to this geometry. It is important to remember that hybridization was devised to rationalize experimentally observed molecular geometries. The model works well for molecules containing small central atoms in which the valence electron pairs are close together in space. However, for larger central atoms, the valence shell electron pairs are farther from the nucleus, and there are fewer repulsions. Their compounds exhibit structures that are often not consistent with VSEPR theory, and hybridized orbitals are not necessary to explain the observed data. For example, we have discussed the HOH bond angle in H2O, 104.5 degrees, which is more consistent with sp3 hybrid orbitals on the central atom than with 2p orbitals. Sulfur is in the same group as oxygen, and H2S has a similar Lewis structure. However, it has a much smaller bonding angle, 92.1 degrees, which indicates much less hybridization on sulfur than oxygen. Continuing down the group, tellurium is even larger than sulfur, and for H2Te, the observed bond angle is 90 degrees, as consistent with overlap of the 5p orbitals without invoking hybridization. We invoke hybridization where it is necessary to explain the observed structures. (8.3) Multiple bonds. By the end of this section, you'll be able to describe multiple covalent bonding in terms of atomic orbital overlap, relate the concept of resonance to pi bonding and electron delocalization. The hybrid orbital model appears to account well for the geometry of molecules involving single covalent bonds. Is it also capable of describing molecules containing double and triple bonds? We have already discussed that multiple bonds consist of sigma and pi bonds. Next, we can consider how we visualize these components and how they relate to hybrid orbitals. The Lewis structure of ethylene in C2H4 shows us that each carbon atom is surrounded by one other carbon atom and two hydrogen atoms. The three bonding regions form a trigonal planar electron pair geometry. Thus, we expect the sigma bonds from each carbon atom are formed using a set of sp2 hybridized orbitals that result from hybridization of two of the 2p orbitals and the 2s orbital. These orbitals form the CH single bonds and the sigma bonds in the C double bonds. The pi bonds in the CC double bond results from the overlap of the third remaining 2p orbital on each carbon atom that is not involved in hybridization. This unhybridized p orbital is perpendicular to the plane of the sp2 hybrid orbitals. Thus, the unhybridized 2p orbitals overlap in a side-by-side fashion above and below the internuclear axis and form a pi bond. In an ethene molecule, the four hydrogen atoms and the two carbon atoms are all on the same plane. If the two planes of the sp2 hybrid orbitals tilted relative to each other, the p orbitals would not be oriented to overlap efficiently to create the pi bond. The planar configuration for the ethene molecule occurs because it is the most stable bonding arrangement. This is a significant difference between sigma and pi bonds. Rotation around a single sigma bond occurs easily because the end-to-end orbital overlap does not depend on the relative orientation of the orbitals on each atom in the bond. In other words, rotation around the internuclear axis does not change the extent to which the sigma bond orbital overlap because the bonding electron density is symmetric about the axis. Rotation about the internuclear axis is much more difficult for multiple bonds, however. This would drastically alter the off-axis overlap in the pi bonding orbitals, essentially breaking the pi bond. In molecules with sp hybrid orbitals, two unhybridized p orbitals remain on the atom. We find this situation in acetylene, which is a linear molecule. The sp hybrid orbitals of the two carbon atoms overlap end to end to form a sigma bond between the carbon atoms. The remaining sp orbitals form sigma bonds with the hydrogen atoms. The two unhybridized p orbitals per carbon are positioned such that they overlap side by side, hence they form two pi bonds. The two carbon atoms of acetylene are thus bound together by one sigma bond and two pi bonds, giving it a triple bond. Okay. Hybridization involves only sigma bonds, lone pairs of electrons, and single unpaired electrons. Structures that account for these features describe the correct hybridization of the atoms. However, many structures also include resonance forms. Remember that resonance forms occur when various arrangements of pi bonds are possible. Since the arrangement of pi bonds involves only the unhybridized orbitals, resonance does not influence the assignment of hybridization. For example, molecule benzene has two resonance forms. We can use either of these forms to determine that each of the carbon atoms is bonded to three other atoms with no lone pairs, so the correct hybridization is sp2. The electrons in the unhybridized p orbitals form sigma bond or pi bonds. Neither resonance structure completely describes the electrons in the pi bonds. They are not located in one position or the other, but in reality are delocalized throughout the ring. Valence bond theory does not easily address delocalization. Bonding in molecules with resonance forms is better described by molecular orbital theory. 8.4. Molecular orbital theory. By the end of this section, you will be able to outline the basic quantum mechanical approach to deriving molecular orbitals from atomic orbitals, describe traits of bonding and anti-bonding molecular orbitals, calculate bond orders based on molecular electron configurations, write molecular electron configurations for first and second row diatomic molecules. relate these electron configurations to the molecule's stabilities and magnetic properties. For almost every covalent molecule that exists, we can now draw the Lewis structure, predict the electron pair geometry, predict the molecular geometry, and come close to predicting the bond angles. However, one of the most important molecules we know, the oxygen molecule, presents a problem with respect to its Lewis structure. We would write the following Lewis structure for O2, that this electronic structure adheres to all the rules governing Lewis theory. There is an O-O double bond, and each oxygen atom has 8 electrons around it. However, this picture is at odds with the magnetic behavior of oxygen. By itself, O2 is not magnetic, but it is attracted to magnetic fields. Thus, when we pour liquid oxygen past a strong magnet, it collects between the poles of the magnet and defies gravity, as in figure 8.1. Such attraction to a magnetic field is called paramagnetism, and it arises in molecules that have unpaired electrons, and yet the Lewis structure of O2 indicates that all electrons are paired. How do we account for this discrepancy? Magnetic susceptibility measures the force experienced by a substance in a magnetic field. When we compare the weight of a sample to the weight measured in a magnetic field, paramagnetic samples that are attracted to the magnet will appear heavier because of the force exerted by the magnetic field. We can calculate the number of unpaired electrons based on the increase in weight. Experiments show that each oxygen molecule has 2 unpaired electrons. The Lewis structure model does not predict the presence of these 2 unpaired electrons. Unlike oxygen, the apparent weight of most molecules decreases slightly in the presence of an inhomogeneous magnetic field. Materials in which all of the electrons are paired are diamagnetic and weakly repel a magnetic field. Paramagnetic and diamagnetic materials do not act as permanent magnets. Only in the presence of an applied magnetic field do they demonstrate attraction or repulsion. Molecular orbital theory provides an explanation of chemical bonding that accounts for the paramagnetism of the oxygen molecule. It also explains the bonding in a number of other molecules, such as violations of the octet rule and more molecules with more complicated bonding beyond the scope of this text and that are difficult to describe with Lewis structures. Additionally, it provides a model for describing the energies of electrons in a molecule and the probable location of these electrons. Unlike valence bond theory, which uses hybrid orbitals that are assigned to one specific atom, MO theory uses the combination of atomic orbitals to yield molecular orbitals that are delocalized over the entire molecule rather than being localized on its constituent atoms. MO theory also helps us understand why some substances are electrical conductors, others are semiconductors, and still others are insulators. Table 8.2 summarizes the main points of the 2 complementary bonding theories. Both theories provide different useful ways for describing molecular structure. Molecular orbital theory describes the distribution of electrons in molecules in much the same way that the distribution of electrons in atoms is describing using atomic orbitals. Using quantum mechanics, the behavior of an electron in a molecule is still described by a wave function psi, analogous to the behavior in an atom. Just like electrons around isolated atoms, electrons around atoms and molecules are limited to discrete quantized energies. The region of space in which valence electron in a molecule is likely to be found is called a molecular orbital, or psi squared. Like an atomic orbital, a molecular orbital is full when it contains 2 electrons with opposite spin. We will consider the molecular orbitals in molecules composed of 2 identical atoms. Such molecules are called homonuclear diatomic molecules. These diatomic molecules, several types of molecular orbitals occur. The mathematical process of combining atomic orbitals to generate molecular orbitals is called a linear combination of atomic orbitals. The wave function describes the wave-like properties of an electron. Molecular orbitals are combinations of atomic orbital wave functions. Combining waves can lead to constructive interference, in which peaks line up with peaks, or destructive interference, in which peaks line up with troughs. In orbitals, the waves are 3-dimensional, and they combine with in-phase waves producing regions with a high probability of electron density and out-of-phase waves producing nodes or regions of no electron density. There are two types of molecular orbitals that can form from the overlap of two atomic s orbitals on adjacent atoms. The two types are illustrated in figure 829. The in-phase combination produces a lower energy sigma s molecular orbital in which most of the electron density is directly between the nuclei. The out-of-phase addition, which can also be thought of as subtracting the wave functions, produces a higher energy sigma s star molecular orbital um, in which there is a node between the nuclei. The asterisk signifies that the orbital is an anti-bonding orbital. Electrons in a sigma s orbital are attracted by both nuclei at the same time and are more stable than they would be in the isolated atoms. Adding electrons to these orbitals creates a force that holds the two nuclei together. So we call these orbitals bonding orbitals. Electrons in the sigma s star orbitals are located well away from the region between the two nuclei. The attractive force between the nuclei and these electrons pulls the two nuclei apart. Hence, the orbitals are called antibonding orbitals. Electrons fill the lower energy bonding orbital before the high energy antibonding orbital, just as they fill lower energy atomic orbitals before they fill higher energy atomic orbitals. In p orbitals, the wave function gives rise to two lobes with opposite phases, analogous to how a two-dimensional wave has both parts above and below the average. We indicate the phases by shading the orbital lobes different colors. When orbital lobes of the same phase overlap, constructive wave interference increases the electron density. When regions of opposite phase overlap, the destructive wave interference decreases electron density and creates nodes. When p orbitals overlap end to end, they create sigma and sigma star orbitals. If two atoms are located along the x-axis in a Cartesian coordinate system, the two px orbitals overlap end to end and form the sigma px bonding and sigma px antibonding. Just as the s orbital overlap, the asterisk indicates the orbital with a node between the nuclei, which is a higher energy antibonding orbital. The side-by-side overlap of two p orbitals gives rise to a pi bonding molecular orbital and a pi star antibonding molecular orbital, as shown in figure 831. In valence bond theory, we describe pi bonds as containing a nodal plane containing the internuclear axis and perpendicular to the lobes of the p orbitals, with electron density on either side of the node. In molecular orbital theory, we describe the pi orbital by this same shape, and a pi bond exists when this orbital contains electrons. Electrons in this orbital interact with both nuclei and help hold the two atoms together, making it a bonding orbital. For the out-of-phase combination, there are two nodal planes created, one along the internuclear axis and a perpendicular one between the nuclei. In the molecular orbits of diatomic molecules, each atom also has two sets of p orbitals oriented side by side. So these four atomic orbitals combine pairwise to create two pi orbitals and two pi star orbitals. The pi py and pi star py orbitals are oriented at right angles to the pi pz and pi star pz orbitals. To further orientation, the pi py and the pi pz orbitals are identical and have the same energy. They are degenerate orbitals. The pi star py and the pi star pz antibonding orbitals are also degenerate and identical except for their orientation. A total of 6 molecular orbitals result. From the combination of the 6 atomic p orbitals in 2 atoms. And it's those ones. Oh, wait, was that a... Okay. Molecular orbital energy diagrams. The relative energy levels of atomic and molecular orbitals are typically shown in a molecular orbital diagram. For a diatomic molecule, the atomic orbitals of one atom are shown on the left, and those of the other atom are shown on the right. Each horizontal line represents one orbital that can hold 2 electrons. The molecular orbitals formed by the combination of the atomic orbitals are shown in the center. Dashed lines show which of the atomic orbitals combine to form the molecular orbitals. For each pair of atomic orbitals that combine, one lower energy bonding molecular orbital and one higher energy anti-bonding orbital result. Thus, we can see that combining the 6 2p atomic orbitals results in 3 bonding orbitals um, and 3 antibonding orbitals. We predict the distribution of electrons in these molecular orbitals by filling the orbitals in the same way that we fill atomic orbitals by the Aufbau principle. Lower energy orbitals fill first, electrons spread out among degenerate orbitals before pairing, and each orbital can hold a maximum of 2 electrons with opposite spins. Just as we write electron configurations for atoms, we can write the molecular electronic configuration by listing the orbitals with superscripts indicating the number of electrons present. For clarity, we place parentheses around molecular orbitals with the same energy. In this case, each orbital is at a different energy, so parentheses separate each orbital. Thus, we would expect a diatomic molecule or ion containing 7 electrons, such as Be2+, would have the molecular electron configuration sigma 1s2, sigma star 1s2, sigma 2s2, sigma star 2s2, 1. It is common to omit the core electrons from molecular orbital diagrams and configurations and include only the valence electrons. The bond order. The filled molecular orbital diagram shows the number of electrons in both bonding and antibonding molecular orbitals. The net contribution of the electrons to the bond strength of a molecule is identified by determining the bond order that results from the filling of the molecular orbitals by electrons. When using Lewis structures to describe the distribution of electrons in molecules, we define bond order as the number of bonding pairs of electrons between 2 atoms. Thus, a single bond has a bond order of 1, a double bond has a bond order of 2, and a triple bond has a bond order of 3. We define bond order differently when we use the molecular orbital description of the distribution of electrons, but the resulting bond order is usually the same. The MO technique is more accurate and can handle cases when the Lewis method fails, but both methods describe the same phenomenon. In the molecular orbital model, an electron contributes to a bonding interaction if it occupies a bonding orbital, and it contributes to an antibonding interaction. If it occupies an antibonding orbital, the bond order is calculated by subtracting the destabilizing antibonding electrons from the stabilizing bonding electrons. Since a bond consists of 2 electrons, we divide the 2 to get bond order. We can determine bond order with the following equation. The bond order of a covalent bond is a guide to its strength. A bond between 2 given atoms becomes stronger as the bond order increases. If the distribution of electrons in the molecular orbitals between 2 atoms is such that the resulting bond would have a bond order of 0, a stable bond does not form. We next look at some specific examples of MO diagrams and bond orders. Bonding in diatomic molecules. A dihydrogen molecule forms from 2 hydrogen atoms. When the atomic orbitals of 2 atoms combine, the electrons occupy the molecular orbital of lowest energy, the sigma 1s bonding orbital. A dihydrogen molecule, H2, readily forms because the energy of a hydrogen molecule is lower than that of 2 hydrogen atoms. The sigma 1s orbital that contains both electrons is lower in energy than either of the 2 1s atomic orbitals. A molecular orbital can hold 2 electrons, so both electrons in the H2 molecule are in the sigma 1s bonding orbital. The electron configuration is sigma 1s2. We represent this configuration by a molecular orbital energy diagram in which a single upward arrow indicates 1 electron in an orbital and 2 arrows indicate 2 electrons of opposite spin. A dihydrogen molecule contains 2 bonding electrons and no anti-bonding electrons. So we have bond order equals 1. A helium atom has 2 electrons, both of which are in its 1s orbital. 2 helium atoms do not combine to form a dihelium molecule with 4 electrons because the stabilizing effect of the 2 electrons in the lower energy bonding orbital would be offset by the destabilizing effect of the 2 electrons in the higher energy antibonding molecular orbital. We would write the hypothetical electron configuration of He2 as sigma 1s2, sigma 1s star 2, as in figure 8.36. The net energy change would be 0, so there is no driving force for helium atoms to form the diatomic molecule. In fact, Helium exists as discrete atoms rather than as diatomic molecules. The bond order in a hypothetical dihelium molecule would be 0. A bond order of 0 indicates that no bond is formed between two atoms. The diatomic molecules of the second period. 8 possible homonuclear diatomic molecules might be formed by the atoms of the second period of the periodic table, and there they are. However, we can predict that the beryllium 2 molecule and the neon 2 molecule would not be stable. We can see this by a consideration of the molecular electron configurations. We predict valence, molecular orbital, electron configurations just as we predict electron configurations of atoms. Valence electrons are assigned to valence molecular orbitals with the lowest possible energies. Consistent with Hund's rule, whenever there are 2 or more degenerate molecular orbitals, electrons fill each orbital of that type singly before any pairing of electrons takes place. As we saw in valence bond theory, sigma bonds are generally more stable than pi bonds formed from degenerate atomic orbitals. Similarly, in molecular orbital theory, sigma orbitals are usually more stable than pi orbitals. However, this is not always the case. The MOs for the valence orbitals of the second period are shown in figure 837. Looking at neon 2 molecular orbitals, we see that the order is consistent with the generic diagram shown in the previous section. However, for atoms with 3 or fewer electrons in the p orbitals, lithium through nitrogen, we observe a different pattern in which the sigma p orbital is higher in energy than the pi p set. Obtain the molecular orbital diagram for a homonuclear diatomic ion by adding or subtracting electrons from the diagram of the neutral molecule. This switch in orbital ordering occurs because of a phenomenon called sp mixing. Sp mixing does not create new orbitals, it merely influences the energies of the existing molecular orbitals. The sigma s wave function mathematically combines with the sigma p wave function, with the results that the sigma s orbital becomes more stable and the sigma p orbital becomes less stable. Similarly, the anti-bonding orbitals undergo sp mixing, with the sigma s star becoming more stable and the sigma p star becoming less stable. Sp mixing occurs when the s and p orbitals have similar energies. The energy difference between 2s and 2p orbitals and oxygen, fluorine, and neon is greater than that in lithium, beryllium, boron, carbon, and nitrogen. Because of this, O2, F2, and Ne2 exhibit negligible sp mixing, and their MO diagrams follow the normal pattern, as shown in figure 837. All of the other period 2 diatomic molecules do have sp mixing, which leads to the pattern where the sigma p orbitals is raised above the pi p set. Using the MO diagram shown in figure 837, we can add in the electrons and determine the molecular electron configuration and bond order for each of the diatomic molecules. As shown in table 8.3, beryllium 2 and neon 2 molecules would have a bond order of 0, and these molecules do not exist. The combination of 2 lithium atoms to form a lithium molecule is analogous to the formation of H2, but the atomic orbitals involved are the valence 2s orbitals. Each of the 2 lithium atoms has 1 valence electron. Hence, we have 2 valence electrons available for the sigma 2s bonding molecular orbital. Because both valence electrons would be in a bonding orbital, we would predict the lithium 2 molecule to be stable. The molecule is, in fact, present in appreciable concentration in lithium vapor at temperatures near the boiling point of the element. All the other molecules in table 8.3 with the bond order greater than 0 are also known. The O2 molecule has enough electrons to half fill the pi star 2py and pi star 2pz level. We expect the 2 electrons that occupy these 2 degenerate orbitals to be unpaired, and this molecular electronic structure for O2 is in accord with the fact that the oxygen molecule has 2 unpaired electrons. The presence of 2 unpaired electrons has proved to be difficult to explain using Lewis structures, but the molecular orbital theory explains it quite well. In fact, the unpaired electrons and the oxygen molecule provide a strong piece of support for the molecular orbital theory. All right, that's it. Cool.